This lesson is titled Relations and Functions. A relation is a set of ordered pairs. The age and height ordered pairs below form a relation. 18 would be related to 4.25. 14 would be related to 5, for example. You can use this list also. You can set it up in ordered pairs so that you don't have to look at a table. Sometimes one representation is a little easier to use than the other, depending on what you're trying to do with it. So, for example, 24.4 is the same as the point 20 comma 4.4. A function is a relation that assigns exactly one output value for each input value. So, for example, if 14 equals 5, then 14 couldn't equal something else also. It has to always equal 5. If that's true for every value of x, and when we look at points, then that relation is a function. One way you can tell if a relation is a function is by making a mapping diagram. The way to do that is you first list the domain and the range, and then you draw arrows from one to the other. So here's an example. We've got the domain. Remember that the domain is just the x value. So I've got 11, 12, 13, and 20. We show those in the domain. And then the range is the y values, the -2, the -1. -2 has already been used, so we only list it once, and 7. And then we map arrows from each domain value to its range value. So we'll see an arrow from 11 going to -2, 12 going to -1, and so on. So there's 11 mapped to -2, 12 mapped to -1, 13 also maps to -2, and 20 maps to 7. This whole thing right here is a mapping diagram. This relation is a function because every domain or x value maps to exactly one range value or y value. 11 is only -2, 13 is only -2, 12 is only -1, and 20 is only 7. Determine whether this relation is a function. Well, I see -2 maps to -1 and -2 maps to 1, so no, that's not a function because -2 maps to more than one value. Another way to write a function is to use function notation. And notice there's really not that much different here. Instead of saying y equals, we say f of x equals. Everything else is the same. We can also use G or H or other letters instead of F. F, G, and H are the most commonly used, however. We're going to make a table from a function rule. So we're given the function f of n equals -2n squared plus 7. So x isn't magic either. We can put another variable in for that. We're going to use 1, 2, 3, and 4 as domain values. So here's our table. We got n and we got f of n, or n and y, if you will. We can let n equal 1, 2, 3, or 4. And then when n is 1, we go ahead and plug it in. We'd have -2 times 1 squared, which is -2, plus 7, which would be 5. When n is 2, we would get -1. When n is 3, we would get -11. And when n is 4, we would get -25. So this is a table of values for our function f of n. We're going to make a table, and I'm not going to do as much work as they did. I'm just going to make a simple table here, x and y. So we call this a t-table because it looks like a lowercase t. I've got my x values, I've got my y values. They want my domain to be 1, 2, 3, and 4. Those are my x values, 2, 3, and 4. And then we just plug these in and see what we get. So when x is 1, I'd have 8 minus 3, or 5. When x is 2, I'd have 8 minus 6, or 2. When x is 3, I'd have 8 minus 9, or -1. And when x is 4, I have 8 minus 12, or -4. So this whole thing is my table of values for that function. We're going to make a table for this function. So again, let's make a little t-table here. They want us to use 1, 2, 3, and 4 for domain values. So we'll have x, we'll have y. 1, 2, 3, and 4. We'll plug in 1. 2 times 1 is 2, plus 1 is 3. And we'll plug in 2. 4 plus 1 is 5. We'll plug in 3. 6 plus 1 is 7. And if you see the pattern here, we would expect a 9 here, right? 3, 5, 7, 9. 4 plus 1 is 8, plus 1 is 9. So there's my table of values. We're going to find some range. Range is the value that all the y's are given all the x's. Okay, so my domain is -3, 1, and 4. They want us to find the range that goes with that. So if we plug -3 into here, we get 14. If we plug 1 into this function, we get 2. It's kind of the same thing we were doing with the table. It's just a different way to show all that information. When we plug 4 in, we get -7. So my range, when I plug in a -3, a 1, and a 4, I would get back a -7, a 2, and a 17. Remember that table we had on the previous slide? It doesn't want to show it to me. So we had a table on the previous slide. If we set this up in a table, we would see x, we'd see y. They told us to use -3, 1, and 4, and what we got was -7, 2, and 14. So if you're working in tables, this information right here, that's the range. This information over here, that was the domain. So if you can do a table, you can do this question where it says, here's a domain, what's the range? It's just how you write your answer out that's maybe a little different looking. For this problem, we're given a domain and a function that says, what's the range? Let's just go ahead and do a table here. So we've got x, we've got y. We can use -2, 0, and 5 in our domain and see what we get. If I plug in -2, -2 minus 6 is -8. If I plug in 0, I get -6. If I plug in 5, I get -1. So my domain, or excuse me, my domain's given, my range is -8, -6, and -1. Let's check that with what they want us to get here. There's the answer they wanted us to get. -8, -6, -1. Exactly the same thing we got. So if you can do a table, you can find a range. Let's look at the next problem here. They gave us y equals -4x. Well, if I put in -2, I'm going to get 8. If I put in 0, I'm going to get 0. And if I put in 5, I'm going to get -20. So I should see what? 8, 0, and -20. 8, 0, and -20. It doesn't matter the order we put these in. A lot of times they'll put them in least to smallest. I listed them in just the order I got them. So either way kind of makes sense depending on how you're working. And the last function we're going to deal with here is t squared plus 1. So I put -2 in for t. That gives me 4 plus 1 is 5. I put in 0 for t. I get 0 plus 1 is 1. And then I put in 5. I get 25 plus 1 is 26. So they're probably going to list it as 1, 5, and 26. 5, 1, and 26 is the order I got them in, but they'll probably list it in increasing order. Either way is fine. It's just a set of values when we list that. Okay, now we've got a series of questions here. It says use a mapping diagram to determine if each relation is a function. Well, let's just take a look. Notice I have 3, 7, and 3, 8, and I have 3, 1, and 3, 4. All the x is 3, and we get a bunch of different y's. So no, that's not a function. Anytime that I have a different value for y for one x, like 3, 7, and 3, 8, that's not a function. Here I've got 6, 5. I've got 5, -8, and 5, 5. That's not a function. You try this one real quick. Notice how all the x's are different? So yeah, that is a function. Try this one real quick. You see the 4, 2 and the 4, -2? Different values of y for that 4. That's not a function. Same thing. The directions look a little different. They're referring to the graph of this, but you can use the same exact technique you used here to do this one. You got it yet? We got 2, 3, 4, 5, all different x's. That's a function. How about this one? You see the 5, 0 and the 5, 1? Not a function. How about this one? 3, -1 and 3, 2? Not a function. And finally, -2, 3, -1/2, and 4, those are all different. That's a function. Determine whether each relation is a function. If it is, state the domain and range. Let's see, I got 1, -3, and 1, 3. 1 goes to two different things, so that is not a function. How about this one? All the x's are different, so it is a function. The domain is just going to be all these values. The range is going to be that value. So yes, the domain is -4, -1, 0, and 3, and the range is just -4. I like to say which is which, so when I write an answer like this, I like to put a big D in front of this so I know that's a domain, and put a big R in front of that so I know that's a range, so there's no question about what I'm listing there. Determine whether each graph is the graph of a function. The key here is if we can take a vertical line and pass it across this graph and never hit more than one point, it's a function. So imagine this vertical line. If I could just grab it and pull it across the graph, would it ever hit more than one point? Well, the answer is no. It always just hit exactly one point, and that makes it a function. So yeah, that's a function. How about this graph? If I pull the vertical line across here, would it ever hit more than one point? Well, yeah, in lots of places it hit more than one point. So no, that is not a function. This is called the vertical line test. And how about this graph? If I had a vertical line that I could pull across here, just grab a hold of and just pull it across the graph, would it ever touch more than one point? Well, no. It would only hit one point at a time. So, yes, that is a function. Determine whether each relation is a function. A, B, C, and E, those are all different x's, so that's a function. How about this one? Notice CD and CA, different values. So we'd have to say, no, that's not a function. How about this one? CCCC, no, that's not a function. Last one, A, B, C, D. Yep, that's a function. All different x values, A, B, C, and D. All right, go ahead and pause the video right here, try these problems, and then press play to see how you did. Okay, for number 1, you should have gotten a domain of -4, 0, 1, 2, and 3, and a range of 0, 1, 3, 4. For part B, you want to say, yep, the relation is a function. For number 3 down here, you should have gotten -9.5, 1, and 7. For number 2A, you would say no, because it would fail the vertical line test right along here, and also right along here. We hit more than one point. And for B, you would say yes, because there's no way I can draw a vertical line and hit more than one point. That's our learning target for this lesson. I'll see you in class.